Let's start with quite a simple example. Let f of t equal e to the 3t. Let's find f of s. Well, f of s is this integral. Let's just write it down, substituting e to the 3t for f of t, little f of t. We get the integral of e to the 3t, e to the negative st dt, integral from 0 to infinity, giving us, when we combine these exponential functions, e to the quantity 3 minus s t dt. And our antiderivative is simply 1 over 3 minus s times e to the 3 minus s t. Our definite integral is the change in that quantity from t equals 0 to t equals infinity. Now at t equals infinity, e to the 3 minus s times t approaches infinity, and our integral diverges, so we don't really, we can't get a function f of s if s isn't at least as big as 3. So we'll make a note here. S must be greater than or equal, could be equal, because if s equals 3, the exponent is 0, we get e to the 1. That's okay. Of course, down for t equals 0, we're going to get e to the 1, so we get 0 for our Laplace transform. And maybe I'd better say that s has to be greater than 3, because of course the denominator here would be undefined if s was equal to 3, and we'd have a problem there. So I should have left that just greater than instead of greater than or equal. I'll fix that in a minute. But we see that, okay, the limit at infinity, as long as s is bigger than 3, we have a negative multiple of t, and e to a negative multiple of t approaches 0 as t approaches infinity. Now at t equals 0, of course, we get e to the 0, which is 1. So what we get is 0 minus 1 over 3 minus s, which is 1 over s minus 3. This gives us what we call a Laplace transform pair. F of t is e to the 3t, and f of s equals 1 over s minus 3. Okay, now that's pretty easy. It's not always easy to do these integrals, and things get a little bit more complicated, but there's nothing here that's not well within the realm of what you learn in a decent first semester calculus course, first year calculus course. Okay, that was a pretty easy integral. And let's do another example. Let's let f of t equal e to the alpha t. Here we did e to the alpha t for alpha equals 3. The integral we get for e to the alpha t is going to be very similar, except instead of 3, we're going to end up with alpha here. And you can see that this exponent is going to be negative as t approaches infinity, as long as s is greater than or equal to alpha. So let's write out the details of this and look at what our Laplace transform pair is. See if you can figure it out before I do it. So we have the integral from 0 to infinity of e to the alpha t, e to the negative ts dt, which is going to be the integral from 0 to infinity of e to the alpha minus ts dt, which is then going to be 1 over realized when I started to do this, I'd written the t, I transposed the t and the s up here, obviously. I don't know if I said it right or not, but it's e to the alpha minus s times t, and that's real obvious if you look at this correctly. So we get 1 over alpha minus s e to the quantity alpha minus s t. Changing that quantity between t equals 0 and infinity. As t approaches infinity, as long as s is bigger than alpha, this works. And we get 1 over s minus alpha, alpha bigger than s. Notice that I fixed this up here. I don't know if I pointed that out. So again, we have another Laplace transform pair. F of t equals e to the alpha t. F of s equal 1 over s minus alpha. This allows us to Laplace transform any exponential function.